different point because the photon comes in, it hits all your material, and each of the point, all the material that experience photoionization will emit a photoelectron wave. So in fact, instead of the incoming electron waves scatter off, bounce off your material, you now bring your emitter right inside the material, and your emitter is your material itself, because the emitter is the one that emits the photoelectron waves. Okay? And that is a little bit different, and this is known as local structure, because you now don't care about, you only care about your immediate nearest neighbor, right? Because that generates the wiggles. You don't care about 4 or 5 neighbors away, because you will not see them, because they are so, because if you look at my Fourier transform, right, I usually see one major peak, and then I see some, maybe 1 or 2 other weaker peak, and then I don't see any more, because these little wiggles could be noise. I have to be careful about that. Okay, so really you are only sensitive maybe at the most 3 nearest neighbor, and then you are out, because you're not sensitive anymore to this. Okay, so this is why we call XF a local probe, is because it probes the local structure, a single atom inside your structure, immediate local neighborhood of that's the emitter that you have. Okay, so that's the basic point about this, and furthermore, the analysis for Li and Sane, right, near structure. Because they're dealing with low energy electron scattering, multiple scattering must be considered in order to model the intensity that you got. Whereas in XF, single scattering theory is enough. You can generate Fourier transform, is quite wonderful in that sense. So here I show an example of this material for XF, example of bare metal. So let me see if I can go up. It's quite nice because it is really quite a wonderful technique in many ways. If you look at the first part, the black lines here, the bottom one, that corresponds to bare metal, FCC, platinum, palladium, metal, that you have this wiggle. This corresponds, of course, to the structure, physical structure of palladium itself. And then, if you look at the green curve, right, the green curve corresponds to palladium chloride material, and you got a totally different XF structure. In this case, well, we are talking about same structure, right? Because we are talking about within 50 volts, so you see a different same structure cut from the palladium. You can see the electronic. The material itself, the chemical identity would matter, would change the same structure, the near structure that you see there. And then the other two curves correspond to palladium colloid material. So you could have, this is nanoparticle now, right? You're talking about a few atoms, palladium, platinum mixed together. You create hybrid colloid particle in here, and you can see again the same structure is quite different. It really tells you something about the chemical nature of the material itself. But of course, to identify them is not so easy. Okay. And on this side, I try to show you how you can actually do in a more precise way, not just single electron scattering calculation. You can do more elaborate calculation, right? So here, one way is that, okay, so the red curve is your experiment, okay? And you have some theory, right? You can in fact calculate this chi curve, no problem. You can calculate this chi curve, and it is the darker curve, not the, I think it's blue or black, you can't see from here. And you can see if you can do really quite good modeling. It overlaps almost completely on this red curve, which is your experiment curve, and the bottom line shows the residual, the difference the area, if you like. And here's the Fourier transform from this curve to this curve, right? And you can see really overlap. And because you have a model to generate this back curve, you know exactly what the structure is. Because if you can say that they agree with your experiment, then you got it. You have the complete structure determination. Because in order to generate this back curve, you have to start off with a model of your material, and then you apply the field to generate this chi curve. And ultimately, if you do a Fourier transform, so you get Ft from here, then you got this position, right? These are nearest neighbor distances in your material inside. So you usually have the first nearest neighbor, second nearest neighbor, and so forth. Okay. So that's except now. But except you're talking about X-ray, right? What happened? Well, again, it's the simple except process. Photon comes in, photons out, and you're measuring the intensity change of this photon. Okay, intensity change of this photon. Right. So here the intensity change is different. Even mu is the same, but the intensity change is different. And the whole photon penetrate your X-ray. X-ray can penetrate material deep into the material, so it goes through your entire material. So anything that can undergo for the emission process could affect what the photon that come out. Okay, and so how do I know that I want to filter out just the information of the surface of this part that I got? I don't want the bulk. Okay, so the blue or the black. The black is what I want. I want the surface area of what I want. I don't care about the bulk part, right? So how do I get that information out when I do XF? Okay, some guy discovered that, well, all we have to do really, instead of measuring the photon in, photon out, so you have I naught I, like this, as a function of x mu, right? As a function of mu, my photon wavelength, like that. All I have to do, I don't need to measure the outgoing photon intensity, really. I don't need that. I just need to measure something that's proportional to this, right? Because I don't really care about the absolute number between these two, because all I want is the chi curve, is how they, because I have to cut out my background anyway. So I can use any signal, right? Any signature from the material after this excitation that I know is proportional to my photon intensity. Okay, so and that's very easy, because essentially any electronic transition is proportional to my photon intensity, my incoming photon intensity, and how much absorbent that I have. So what people find is that they can measure the total electron yield, TEY. This is one of the jargon that you may see, which correspond to any electron that come out. All the electron, I just measure any electron that come out, and because I know that the more intensity that I have, right, the more intensity get, more, if you have more material that you got, you would expect more total electron emission, right? Or I can be selective of all these electrons that I come out. I can select one type of electron that come out, maybe the OJ electron, or maybe the full electron of 1s orbital or something like this. I can select them based on my kinetic energy of my electron that come out. And this is called partial electron yield. Okay, so this is total electron yield, partial electron yield. So essentially, you are detecting these electron yield that come out from this material. Now, why I care about electron yield? Well, you remember the mean free path, right? This is why we talk about this mean free path quite a lot. Electron is nice because electron can only come out near the surface, because even though electron emission could occur deep in the bulk, they lose so much energy when they make it to the surface, you don't see them. Okay, so the mean free path control, essentially tell me, if depending on the energy I got, I could be very surface sensitive if I measure electron yield, because it just, those electrons that come out has to come out from near the surface region, because the one that in the bulk did not make it, cannot make it to the surface, and therefore I don't detect that. Okay? So the key here is that I would take my information, I would select my measurement so that I only detect electron coming out from near surface, called partial yield measurement. Okay? And here's an example of how you do that. So here you have classic XF or surface XF, okay, SAXF, surface XF. So you have bulk material copper iodide, which is just a salt, right? So you can sprinkle